Recall that an nth order linear ordinary differential equation is of the following form, where you have all the terms. Now, in these first couple of sections, we're only interested with the first order linear ODEs. In the case of the previous section, we only dealt with the first order just having the first degree term. And generally, we simplified it by dividing the a1x over and treating that as just g of x itself. And we even went further and multiplied h of y and had a case of separable variables. But for this video, the focus is going to shift to the first order, where it's not just including the first degree term, but it's also including the 0th term, as you can see. And again, we will clean this up by dividing the a1x over, so we have the derivative by itself. And it becomes p of x for the other. So we proceed. So we have our equation. When g of x is a function, it is known as non-homogeneous. But when it is 0, it is known as homogeneous. So let's get to solving these. How would we solve the homogeneous one? Well, again, the beauty of the homogeneous is, since we have the 0, it looks like in our previous videos, is separable variable. So the idea is to separate the y's and the x's on opposite sides. So step 1 in achieving that is subtracting the p of x y over, dividing the y and multiplying the dx, integrating, and upon doing that we get natural log of y, and then the capital P is just a notation to specify that is an antiderivative upon solving. Then we have the constant, of course. So in order to get y by itself, we can go ahead and take e to the power of on each side. That gets rid of the e natural log, and we have the y by itself. I did a subscript of h to represent that it is a homogeneous. Now let's go ahead and solve the non-homogeneous. So for the purpose of brevity, let's replace p of x and g of x with just p and g, and let's make dy over dx just y prime. So when you look at this, right away you can see that the structure of this y prime plus py looks a lot like the product rule. So the technique here, or the insight here, is to reverse the product rule. So here we see that we are in the right-sided form, but the insight is if we simplify to the left-sided form, then we can sort of undo this product and get the y by itself. So that is what we will attempt to do. So realizing that, we multiply u on each side, and right away we can see that u p y is supposed to be the u prime y if you want to make it like the product rule. So we see that. We write it as d over dx, and upon solving, I'll let you solve it. It's just a separable variable. We've done this a million times, so you should get u equals a constant e to the p of x, where p, the capital P again, represents the antiderivative. And this u, by the way, is known as what we call the integrating factor. Okay? So now that we have completed the product rule, we go ahead and reverse it. So we have uy prime equals to ug. We integrate on each side, and then once we integrate, we have uy by itself, and obviously we get the constant. We divide the u over, we substitute for the u, or the integrating factor, we distribute, we cancel the constants. At the end constant, c1 over c can be recombined into a single c, and then we rewrite the e to the px back to the numerator to make it more cleaner as a negative. And this right here is the solution to the non-homogeneous. Now, one thing you can notice is the reason why we did the homogeneous first is there's this pattern you'll be noticing, is that at the very end, what do we have? We have the homogeneous term inside the non-homogeneous solution. So what non-homogeneous will always be, it will be a solution of the homogeneous, but then the remaining, what is left, will be what is called the particular solution. Okay? Now, one thing you may have noticed, if you look at the solution, it does look there's quite a bit going on, and it does look kind of messy. And memorizing this would be a headache. Now, the goal here is not to memorize this. The goal is to work out this whole process each time. So how do we summarize that? Well, let's summarize it. Well, first step, what we do is, we notice that we multiply by the integrating factor to resemble the product rule. That's what we did first. The second step is to integrate, undo the product, and by dividing the integrating factor. Okay? And the third step is to obviously solve for the integrating factor. And then finally, the fourth step is to substitute the integrating factor, simplify the equation, and then solve it. Generally, these are the 4 steps you want to follow. Okay? So now let's move on to some examples. So for our first example, we have y prime plus 3x squared y equals x squared. First, in order to recognize that it's a first order linear equation, we have to see if it's of the following form. And indeed it is, because we can recognize that 3x squared is p of x and x squared is g of x. So we proceed with our technique. We multiply the integrating factor, and in order to make it like the product rule, we recognize that u prime y has to equal this. So we let u prime equals 3x squared u. Again, u prime can be rewritten. We divide the u over, multiply the dx over, integrate. And then we have natural log u equals x cubed. And then from there you should get u equals c e x to the cube. Now, this looks like the form that we got when we were going over the technique, where we had u equals a constant e to the p x, where p of x was just the antiderivative, the capital P was just the antiderivative of the lowercase p. Obviously, in this case, this follows because the lowercase p was 3x squared, so the antiderivative should be x cubed, which in this case, they match. So, further moving on, we reverse the product rule. We have uy prime equals ux squared. We integrate. And upon integrating, we get the constant. We divide by u. We substitute for u, or the integrating factor. We cross out the c's. And upon doing that, we get this. Now, here, how do we solve this integral? Now, the trick here is, one thing we can notice is that right away, if you have x cubed equals some variable v, then x squared, obviously we can kind of see that's going to be the derivative. So we proceed, we let v equals x cubed, again dv equals 3x squared dx, and then if we divide the 3 over, we realize that we can substitute for the x squared dx, which is inside here, and obviously we can substitute back in v for x cubed. So we go ahead and do that, and we get this. Now, next is we integrate a simple integral. We get the following, and we substitute back in for v. We cross out the e to the x cubed, and then we have our solution.